Hello everyone, and welcome to another web lesson. You notice that we start our lesson a little bit differently today. We're in a simulation. So what we have is a reaction being conducted in two different syringes. All right, and you can see the reaction that's on the screen there. It's the synthesis of dinitrogen tetroxide from the combination of two nitrogen dioxide molecules. So we've looked at equilibrium, how to calculate concentrations, and we know that in an equilibrium process, there's reactants and there's products left over. What we haven't actually looked at yet is the fact that we can manipulate how much of each is at the end of that equilibrium process when the concentrations level out. So there's many factors that are actually control variables in a lot of experiments that'll shift this equilibrium towards the reactants or the products for our benefit. So let's take a look at this. You can see that the molecule with 3 atoms on it is the NO2, right? And then the bigger molecule is the N2O4. You can kind of watch those bouncing around. Now watch what happens here. As I push in the syringe, I want you to notice what happened to the molecules and their motion. Okay, maybe think about why that happened. While you're doing that, what happened to the pressure when I pushed in the syringe? The pressure would have increased because the volume went down and a force is being applied over a smaller area. Now let's do the opposite. In this scenario on the bottom, you can see an equal amount of the molecules floating around. What I'm going to do is just do the opposite with this. And you can see that as I pulled back on the syringe, compare the motion and the molecule that is present. So when you pull back on the syringe, right, the pressure decreases because you have that force acting over a larger area now. And you notice when there's a high pressure, or the syringe is pushed in, high pressure is a low volume, there's more of the product. When there's a low pressure, there's more of the reactant. And we have to ask ourselves, why is that? And it's very important because if we learn how to manipulate the conditions, we can manipulate the equilibrium reaction to produce more products or more reactants based on what we want. And you might think, well, why would you want more reactants? Well, let's assume that this is an environmental pollutant or a toxin, and it's present in a greater equilibrium. If we can change the conditions for it to form a less toxic or a less harmful reactant, we can do that and collect it instead. On the other hand, if we're looking for the product of a reaction, we'd like to force its production, so we would want more of a first scenario here. All right, so with that in mind, let's look at why this happens now. All right. So we call this process LeChateliers's principle, and it's named after the scientist that noticed these relationships between the control variables and how far a reaction proceeds to completion. So what we're going to aim to do is identify stresses that change equilibrium concentrations. Okay, and it forces that K value, the ratio, to change in favor of either the reactants or the products. Once we know what the stresses are, right, we'll just start by stating them. We'll look to explain how a system responds to a stress. So if I increase the pressure on a system, what will it do? It won't stay the same. It'll either turn into reactants or it'll turn into products, right? And why it does that is to alleviate the stress. And you think of it like this. If I turn down the temperature in the room, you'll probably put a coat or a sweater on. You respond to undo the change. So if the room got hot, you want to cool down. Vice versa. If I heat up the room, you might take that sweater or jacket off. The room heats up, you want to cool down. A chemical system is the same. If the pressure goes up, it wants to reduce the pressure by changing itself. So it's really neat to see how it responds without having any kind of intelligence. It's just the stress placed on the bonds in the scenario causes them to interact differently. So the ratio is K. That defines at equilibrium, again, when the process stops or it's in dynamic equilibrium, right, where the concentrations don't change anymore, what there's more of, reactants or products. When that system is disturbed, right, and we call a disturbance a stress, the system will adjust. So think of it there like you in a hot room or in a cold room adjusting to that temperature to do the opposite. And that's what the stress represents. So the stresses that we'll look at we'll state next. right? And we need to remember that at equilibrium, we have some product and some reactant. So let's look at this graph here. If we had to estimate K, right, based on this here, you'll notice that, and again, please pause and try these questions yourself, but the reactants decrease and the products increase. So these are the reactants and this is the product. The reactant, remember it's products over reactants, is greater. So K in this case will be less than 1. Right? We could actually calculate what it is based on these numbers off to the side. So C looks like it's 1.5, and B looks like it's at 2, and A looks like it's at 2.5. Now we don't know the coefficients, so we can't calculate it, but we could assume they were 1 and come up with a number for it. So what we're saying is once these concentrations level off, that is the equilibrium scenario. And remember, it's dynamic, so they're always changing. One molecule changes to products, one molecule changes back to reactants, right? And they exchange, so the concentration stays the same. Now, when they reach this scenario, if we poke it, we just change something about it, it's not going to like that, and it's going to respond, right, by adjusting its ratio. So it'll change because the ratio is specific to a temperature and pressure. So let's look at some of those. Three variables we'll look at. These are called stresses, right? Factors. These are the stresses that we will change or will place the system under. We will change concentration, we can change the temperature, or we can change the volume and the pressure, which you've seen already. So let's explain what happens now in each of these. For concentration, if we increase the concentration of any substance, the equilibrium will shift to consume the added reactant or product. And vice versa, if we take some away, the equilibrium will shift to the side that produces that product. Now the key word here is shift. And what shifting means, and you can see this at the bottom here, it describes which way the reaction goes to undo that change. So if I decrease products, again, the reaction wants to do the opposite, so it's going to produce products. It will shift towards the right. Right? So shifting right means forming more products. Shifting left means it's doing something to generate more reactants. Right? So reactants are formed versus products are formed. And that's how a system responds to concentration. You can't see me, but I'm doing air quotes because it's not intelligent in any way. It just knows that there's a stress on it, and by turning itself into more reactants or more products, it can alleviate that. So if we look at this example here for concentration, we've got the Haber-Bosch process. So this system, initially, at T0 is at equilibrium. And again, we've talked about this before. T0 is read as T0, right? And that's before the process begins. So it's at equilibrium because the concentrations are changing. But then if we look at time 1, to this system, nitrogen was added, increasing its concentration and stressing the ratio. So what happens? Well, you'll notice that because nitrogen is a reactant in this product, its concentration goes down. Hydrogen's concentration also goes down, but ammonia's concentration goes up. So what that means is that the system responded by turning the extra reactant into product. So what we say is that this system shifted right. And in technical terms, what it did is it turned the extra reactants into products. So that brought its concentration down, it brought the product concentration up, and now the ratio is still the same. Okay, so the change is to establish the same ratio. Okay, so that's what's happening there. Because the concentration changed, we changed the value of K, but by turning the extra reactant into product, the ratio was brought back to normal. And that's what it's all about. If we had removed nitrogen from that system, think of it like sucking it out with a straw. The system would think, you took away some nitrogen, I need that back. So it will turn products into reactants to get extra nitrogen there. All right, so it's all about undoing the change that we've done. So next up is temperature, and this is just a summary of what happens. There's a lot of different scenarios, all right, and you can, sometimes it's easy to memorize things, but you can also understand it. If you think of temperature as thermal energy, you can think of it like the concentration of heat, right? The more you add, it shifts either towards or away from it. So here's the summary of those, and we'll look at an example here. So given the reactions, we have nitrogen combining with oxygen to form nitrogen monoxide. This is an endothermic reaction. So if we take this energy term, and you can see by the comma this image is from a European textbook. Okay, we would use the decimal there for 90.4. Okay, so endothermic reactions have energy on the reactant side. Now the question is this: if we increase the temperature, we made this reaction hotter, what's it going to do? Well, it wants to cool itself down. To do that, it has to get rid of that energy. So what it does is it turns the bonds it has into different bonds. So what we're doing is increasing temperature. We'll just put that there. So the system is hot, and it has two options. It can shift either left or right. So if it shifts left towards the reactants, it generates nitrogen, oxygen, and energy, which means the temperature is going to go up even further. But if it shifts to the right, it turns some of that extra energy and it fixes it into a molecule, so it's gone. So it lowers its temperature by hiding energy in the bonds of the molecule. So in this case, we would say that it shifts to the right, it turns energy into a product, and then that brings the temperature back down a little bit. So it'll never completely undo the change, but its goal is to minimize the effect that it has. All right. If this was an exothermic reaction where energy is generated as a product, it would want to hide that energy by turning it into a reactant and then making it disappear. Lastly, the stress that we can control is volume and pressure. So this is related to Boyle's law in the statements that the concentration is related to its pressure. All right, so Boyle's law stated that the pressure and the volume are inversely related. Right? It was this: P1 V1 equals P2 V2. You can think back to the combined gas law for that. So if we increase the volume, we decrease the pressure. Right? If we decrease the pressure, we increase the volume. And that's all stated here. So how does a system respond to that? That was like the first example that we saw. In this case, if we increase the volume, we decrease the pressure. Right? So if I went back to this website, that would be like pulling back on the syringe. Right? So if I have my syringe container, I'd pull out on it, decrease pressure, and you can try this if you have a syringe at home. Hold the end with your finger, pull back on the plunger, and it sucks itself back in because it's almost under negative pressure. So what the pressure does is it affects the concentrations specifically of the gas molecules. So it's very simple. When you change the volume or the pressure, equilibrium will shift to the side with the larger amount of gas molecules to fill the space. So if we increase volume, right, the pressure goes down. To increase the pressure, the molecules take up more space by turning into the reactants or products that have more of the gas molecules. Okay, and then the vice versa happens there. So let's go back to the example here. Right, and if I just set this approximately normal again. So both of these are gas molecules here. On the reactant side, you have two NO2s, and on the product side, you have one N2O4. So the size of it doesn't really factor in here because we've got fairly small molecules. If I pull back on the syringe, I've increased the volume, so I decrease the pressure. And you can see that it turned into reactants. If I push on the syringe, the pressure goes up and the volume goes down, so it turns into the products because there's less molecules on the product side. There's only 4 versus 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this case. Sorry. There's 10, right? So more molecules can occupy more space. When there's less space, the molecules turn into the smaller forms, the smaller numbers, and there is 5 there. That's my mistake. Right? So it responds with the stress to do the opposite. That's our main understanding for this. So if we look at ammonia, and again, this is related to the Haber-Bosch process, as the piston goes down, the pressure increases, right? Increase the pressure because we decrease the volume. So it'll shift to the side with less gas molecules because there's less space to occupy. There's 4 gas molecules on the reactant side and 2 on the product side. Okay, so the smaller volume means that there's an advantage to having less molecules because they take up less space. Doesn't mean there's none of the reactants, there's just less compared to when it's at a lower pressure and a larger volume. It shifts to the right so it can take up more of that space. Okay, so changes in volume affect pressure, which are what affect the concentration. The volume itself doesn't affect the concentration of a gas, but the pressure does. All right, and this is specifically for gas molecules. We would only count those when comparing. Now, there are some things that don't affect equilibrium. Number one is a catalyst. Okay, a catalyst is not used up in the reaction, it just affects its rate, so it's not going to determine if there's more of something there. It'll just help it reach equilibrium faster, but it won't actually affect how much of it there is. An inert gas, think of this as a noble gas, something that doesn't react with everything there. Okay, at a constant volume, it'll occupy space, and it'll change the concentration of the reactants and the products, so there's no advantage to changing either or. Okay, so when that happens, the equilibrium does not change and the reaction, the concentrations stay as they are. So let's go through an example for this system here, combining a bunch of the different stresses. Okay, so here's our system, here's our enthalpy change, because that'll be important for determining how temperature affects it. What happens if SO2 is added? Right, and if you've tried these and you're checking your answers, I'll go through them. If you haven't, please pause now, try these, and then come back. So SO2 is a product. If we add SO2, right, we've increased the concentration of the products. The system wants to turn the extra products that we gave it into reactants. It wants to do something with it. So what happens is it will shift to the left and turn the products, and I'm just using short forms here, please be as specific as you need to, into reactants. That lowers the concentration of the products, raises the reactants, and it ends up keeping K the same. Pressure is decreased by increasing the volume. So a decrease in pressure means it will shift to the side, it'll produce the side that has more molecules, because the container is larger now. So there are 2 reactant gases. Right, we'll say there's 2 reactant gas molecules, and there are 3, we'll just say versus, like it's a battle, versus 3 product gas molecules. So in a larger space, we want the side with more, so we're going to say it shifts to the right and produces more products. Okay, in this case, produce products to increase the pressure. And again, it offsets the change. C, the pressure is increased by adding neon gas. Well, neon gas is inert. It's a noble gas and it doesn't react, so there's no shift. We won't change what the concentrations are, and there won't be any changes. D, what happens if the temperature is decreased? So that means it's made colder. So think about what happens to you. If you're colder, you want to warm up. So let's look at the enthalpy change here. It's positive, which means this is an endothermic reaction. So energy goes on the reactant side. So for this reaction, we ask, how does it generate heat to warm itself up? Well, it does that by shifting towards the reactants, because by turning products into reactants, it releases energy. So it's going to shift left, and we'll just leave it at that, to release energy. So the reverse reaction is exothermic. It gives off heat, but the forwards reaction would consume heat and it would make it colder. Okay, so hopefully this is helping clarify a few things with the explanations. If oxygen is removed, right, we decrease the concentration of oxygen. It's like we took it away from the system, and it says, no, I want that oxygen back. So it's going to shift towards the product side and generate more oxygen. Okay, so the concentration of the products will increase. And that's all of them. So it's not like it just picks all of them, or sorry, one of them. We should be specific there. It's when it shifts towards the product side, all the products increase and all the reactants decrease because the reactants turn into the products. So that's an application of all the different shifts of an equilibrium, depending on what we're looking to do. So in this case, draw concentration versus time graph if F2 is added from the equilibrium. Represent all the molecules on the same graph. So let's just say K is less than 1 in this case. Right, so the reactants are favored. Right, again, think products over reactants. Less than 1 means the denominator is larger. So if I've got this, I've got temp time, I've got concentration in moles per liter. Right, the reactants, whatever they are, we've got bromine, we've got fluorine, and we've got bromine pentafluoride. Okay, so they've reached equilibrium, right? Their concentrations aren't changing anymore. And what we're saying is at some point in time, we add fluorine, so its concentration spikes. So if we increase the concentration of fluorine, remember the reaction wants to undo that, so it's going to shift to the right. Okay, and we think, what does that mean? Well, that means it's going to form products and it will lose reactants. So all of the product concentrations increase and the reactant concentrations decrease. So now from here, fluorine will slowly decrease. We're just sketching. It won't go back to its original level. Bromine will also decrease, but there's no spike because we didn't change that, because it's a reactant, and the products will increase. And then a new equilibrium is established. Again, because the concentrations will balance themselves out. All right, so when one product forms, they all form, and we lose reactants. And when reactants form, we lose products as the opposite. Okay, so that's what the graph is describing. If we'd like to try that again, one more example, right? We've got this example here. So let's do a concentration versus time graph. We've got moles per liter, right? And again, we'll assume that K in this case is greater than 1, so we have more products than reactants. Right? So let's establish the equilibrium. We've got that there. We've got our first reactant for water vapor. We've got our second reactant, and then there's our product. So at equilibrium, right, just showing the change here. Okay, we'll just mark that off as some point in time. We remove HOCl. And it doesn't matter, at this point it's not important how we do that, it's just the fact that we do it. So if you remove something, its concentration decreases. Right? So what we've done is we've decreased the concentration of a product. The reaction wants to replace that product, so it's going to turn some of the reactants into products. Okay, so we're going to say in this case, it will shift right, form more of the products, and it will use up reactants, which decreases their concentration. So the products will increase again from that drop in concentration, and we'll lose reactants to do that. And then once again, we'll reach a new equilibrium with different concentrations, but the same K value. Okay, that's the whole point of the shift, to reestablish the value of K. If the concentration goes down, we have to lower the concentration of the reactants as well and raise that product concentration a bit. So the value of K is now what it was before that change happened. Okay, so the K value tells us a lot about a system and how well it responds to stresses. There's lots of handouts for this. Right? I'd like you to identify what the 2 major stresses were that optimize the production of ammonia and why it's important. Okay, it's related to our agricultural industry. And then there's a few questions in the textbook to try as well, focusing on which way a reaction will respond to a stress. So it's very important to understand what the stresses are, how they affect a reaction, and be able to predict this And then now we're looking at optimizing industrial processes so we can do something on a practical scale with it. So thank you for watching, and I hope that cleared up what the stresses are and how a system replies to them.